Hello everyone, my name is HengKai, and today I'll be presenting on my final year project, Mesh RCNN++ for 3D mesh generation from single to multiple views. Inferring the 3D structure and geometry of scenes and objects from one or multiple 2D images has been one of the primary goals of image-based 3D reconstruction. In recent years, with the improved progress of deep learning techniques and the increasing availability of large 3D training datasets has led to significant advances in 3D shape understanding using deep learning. Inspired by traditional multi-view geometry methods, this project proposes Mesh RCNN++, a multi-view deep learning shape predictor. Mesh RCNN++ is a multi-view 3D deep learning shape predictor that uses Mesh RCNN as its backbone. Mesh RCNN++ receives one or more color images of an object captured from different viewpoints and produces a 3D mesh model in the world coordinates. Mesh RCNN++ consists of three stages: mesh generation, mesh projection, and mesh refinement. The first stage of Mesh RCNN++ is mesh generation. At the core of mesh generation is a network that extracts regional features from the input image and generates a coarse mesh giving the object's rough 3D shape. Given two input images, A and B, they are first passed through ResNet 50 FPN to generate feature A and feature B. Next, feature A is passed into the voxel-only branch of Mesh RCNN to generate a coarse voxel mesh. The second stage, mesh projection, will receive mesh A and feature B from the first stage. Mesh projection stage will project, translate, scale, and match the vertices in mesh A to the points in feature B. Matrix rotation is performed on mesh A to rotate it into the orientation of feature B. Next, matrix translation is performed to shift mesh AR into the position of feature B. Thirdly, since the distance at which the images are taken may be different, min-max scaling is performed to scale the size of mesh ART to match the size of the object in image B. Lastly, as the number of features extracted from image A may be different from image B, this will cause a mismatch in the final stage. Therefore, vertices in mesh ARTS are resampled to match the number of points in feature B. The final stage of Mesh RCNN++ is mesh refinement, where the output of mesh projection stage, mesh ARTSM, is refined using the features extracted from image B. Mesh refinement stage uses the mesh refinement branch from Mesh RCNN. Here are some meshes generated by Mesh RCNN++. The first two rows consist of the images being fed into Mesh RCNN++, and the last row consists of images of the 3D mesh generated. Next, evaluations was done on Mesh RCNN++ to measure its performance. The standard evaluation matrix for 3D shape generation in recent work were adopted. The two evaluation matrices were used. They are namely F1 and chamfer distance. F1 is the harmonic mean of the fraction of predicted points within certain distance of a ground truth point and the fraction of ground truth points within a certain distance of a predicted point. Chamfer distance is an evaluation matrix for 2 point clouds. For each point in the point cloud, the algorithm of chamfer distance finds the nearest neighbor in the other set and sums up the squared distance. For both evaluation matrices, 10K points were sampled uniformly at random from the surface of predicted and ground truth meshes and were used for computation. For F1, a higher score means better performance, while for chamfer distance, a lower score indicates better performance. Mesh RCNN++ was compared with previously published deep learning methods for single-view shape prediction. Notably, Mesh RCNN++ shows improvement over other single-view deep learning shape predictors, demonstrating the advantages of using an additional image to improve the output mesh quality. Mesh RCNN++ could incorporate the additional features learned from the additional image and use it to refine the final 3D mesh model. On the other hand, single-view deep network like Mesh RCNN had to rely on hallucination to generate the unobservable features, producing rough and undesirable results. Mesh RCNN++ was also compared with previously published multi-view deep learning shape predictors, Pixel to Mesh, and 3D R2N2 to show the improvements of Mesh RCNN++ over existing multi-view deep learning shape predictors. For this experiment, Pixel to Mesh++ and 3D R2N2 both uses 3 images for input, while Mesh RCNN++ uses 2 images for input. Mesh RCNN++ outperform other multi-view deep learning shape predictors in all categories while using lesser images. Mesh RCNN++ was able to produce 3D mesh models with better team structure, such as the bench leg and the chair legs that closely resembled the object in the input image. From the experiments, it could be observed that Mesh RCNN++ was able to produce 3D mesh model with much better surface detail and team structures compared to existing multi-view deep learning shape predictors. In conclusion, Mesh RCNN++ achieved better F1 and chamfer distance score compared to other single and multi-view deep networks. And Mesh RCNN++ was able to achieve state-of-the-art performance, producing 3D mesh models that can accurately capture the surface details and team structures of the objects in the input images. With this, I've come to the end of my presentation. Thank you.